Hi, welcome back. So we're in chapter 6, prediction by RCC and the outline prediction by classification to discuss a new kind of algorithm, and that is the SVM or support vector machine. As we have established essentially in the first introduction about the perceptron of a line, we said this vector should be having one important property to be perpendicular to a certain line. But the actual fact, if we want to look at this problem from a different perspective, well, imagine I have a line like that. So the question was, if I tell you a point, would you tell me, is this point on which side of the line? Is it on the right-hand side of the line or left-hand side of the line? So the intuitive idea of answering this question, I think, was also inspiring to discuss this particular point. I look at the parameter of this line. I have two important parameters. This alpha I have as a vector itself, and this point that I'm talking about and I'm trying to discuss is another vector. And basically it turns out if you take the dot product of this, maybe let's take this alpha and just transpose for convenient multiplication by you will get into a certain scalar, and this value of scalar, it turns out if it is positive or negative, that is a big meaning. So if this happens to be positive, it will be on the direction of this alpha vector. So if alpha vector this direction, it means this point, it is on the direction of alpha. On the other direction, it means any point on this side will be negative. So I hope the intuitive idea behind vector multiplication is clear. So all these information, put them together and try to understand it. It gives you an intuitive way just to answer the question, well, if I give you a point on a line and tell me this point on this direction of the line or on this direction of the line, I hope that idea here is quite clear to you. Now, if we get back to our general example here, I can separate this data point. I could have drawn this line here. I could have drawn another line here. So I could have drawn actually multiple lines that's separating two labels. And a question for support vector machine, which one is the best? And it turns out that this best fit again will be decided based on the choice of this W. Sometimes I call it interchangeably as W or as alpha, but I indicate the same thing. We're getting back to the same framework. So first, we need to define this f of x. Then I'm going to define kind of a loose function. Finally, I want to take the derivative or the minima in terms of the alpha. So since we established this, let's now formulate things quite a bit more intuitively. Let's imagine we are actually striving to pick a very good line. We have a number of them. We said could be like this side, could be like this. But let's imagine that the best one is going to be this one. And how to find this one? It says by finding something called a support vector. Support vector corresponds to a data point. And find out the distance between these two lines. This is called the margin. Imagine there's a line in the middle, exactly lying between these two lines. I can find this line as following. And the other line equation, it should look like this. In support vector machine, this best line have one important criteria, the largest margin or distance, let me say, between the two support vector machine. If you find the largest distance, it means you are getting the best fit in line. You could say, well, that's an easy task. I will find here as far as possible. I keep stretching the line. Maybe I take this line from this point and this line is this point. So the line can go forever. I mean, to the last point here. So we need a condition to control the situation. Also, we need the largest distance. What kind of condition we are looking at? We need to make sure all the point must satisfy the following, that alpha transpose x plus b must be larger than or equal to 1, since we are talking about this. The yellow point satisfy the condition alpha transpose x plus b should be less than or equal to 1. If these two conditions are met, it means we are classifying right. So because if I take this line here, everything in here is one label, everything is in their other label. Shouldn't take you too long to convince yourself that I can literally merge these two conditions. If I take the actual label of yi and multiply by what you are guessing, your alpha transpose x plus b should be larger than or equal to 1. It's actually exactly correspond to these two conditions. I will show you why. Imagine the actual label, it is negative, and my classification is negative. That will lead us to right condition. This is going to be larger than or equal to 1. Imagine if this is positive, and I am guessing positive, this condition again will be right. But if I have like say negative and I am guessing positive, this is not going to be right. So something is wrong. We have to repeat again. So I hope this particular part of the equations makes sense. So once again, we don't want to get away from the actual task. To find this line, maximize this margin. Okay, let's choose a point. We want to measure the distance of this point from a point on this particular line. So we are as sort of taking the projection of this vector onto this distance vector, if you will. Like say this is my x1 and this is my x2, so to speak. This vector of x2 minus x1, because they are vector, multiply them by this w vector or alpha vector, but as a unit vector. And if I make some justification on this equation here, now we have this equation. Let's see what we're going to substitute that equation with. What we want to say, for every y is equal to 1, every positive label, we would have that 1 is multiplied by this alpha, the vector, multiplied by this particular data point, as we said, plus b, should be equal to 1. So we have one term here when the label is positive, and we have one, the label is negative. If we substitute these two values down here, this value will guarantee the greatest distance between any 2 points, and that is complied to the condition. Now here we have maximum. We want the maximum distance. So how can we actually equivalent this to a minimum? Well, if you take just the reciprocal of that, taking the length of w over 2, imagine there is a red point here, and imagine there is a yellow point here. This margin is going to struggle actually to be found. That's why we need to add to our equation like regularizers, constants like c, and that's going to be multiplied by sum of error. This is how many error you're going to tolerate. And this delta here, it corresponds how much error. This value is quantified by how much this far from the actual line. And then I multiply that by a constant, and this constant will quantify how much error I would tolerate. For example, if this a large number, that means you will allow this model to stretch the distance as much as you like. So take this line backward here, you can see a lot of point will be misclassified anyway. It's a small, well, it's going to constrain, but still better than not regularizing the term at all. One more last thing, when we discuss about support vector machine, and like say here some data point, and then we have another class data point in here, it's obviously there's no line can be separable, and this is where you use like some kind of enhancement on the feature itself. They call the tricks of kernel. There are a number of kernels, and I think we have discussed that many times. If I take this x1 and x2 and transfer them to another features, for example, I can transfer x to a polynomial, same for x2 polynomial. You could use also some other kind of kernels. They call it, for example, the sigmoid kernel, another one called the radial basis function kernel, which we discussed very much previously. So that was the principal idea of support vector machine. I have just delivered the intuition mathematically behind the algorithm. The next one, maybe we can discuss the naive Bayes algorithm. That's exactly what we're going to do next. I will see you then.